Уважаеми госпожи и господа, уважаема госпожо председател на Българската академия на науките, скъпи колеги, скъпи ученици, учители и гости, добър ден! Казвам се Антони Рангачев, аз съм математик, работещ в Института по математика и информатика на Българска академия на науките и Математически институт Жусил в Париж. Добре дошли на откриването на поредицата от вдъхновяващи срещи и лекции с някои от най-стъкнатите френски математици на нашето време. Събитието "Защо да станете изследовател" се организира от Института по математика и информатика на Българската академия на науките, Съюза на математиците в България, Ученически институт на БАН, с подкрепата на Френския културен институт и под патронажа на посолството на Франция в България. Срещите, които започват днес и които ще се провеждат всеки ден до четвъртък от 16:30 часа до 18:30 часа, са насочени към ученици и студенти с интерес към математиката. Към тези млади хора, които може би ще поемат по пътя на науката и ще бъдат бъдещите откриватели в математиката. Лекторите ще говорят не само на строго математически теми, но и за своя личен път, трудности и вдъхновение. Идеята за провеждането на това събитие възникна след лекция на професор Тeissier на академичния семинар на БАН преди 2 години. На лекцията присъстваха ученици, които зададоха много интересни въпроси. По това време с професор Teissier вече планирахме провеждането на голяма международна конференция по теория на особеностите в Пловдив, която ще се състои следващата седмица. В непринудена дискусия, заедно с академик Олег Мушкаров, се зароди идеята, че в дните преди провеждането на такива значими конференции за българската математика, може да се проведат срещи между някои от участниците в конференциите с най-младите приятели на математиката в България. Надяваме се този формат, който стартираме днес, да се превърне в традиция. Щастлив съм да отбележа, че днес сред нас са член-кореспондент Евелина Славчева, председател на БАН, член-кореспондент Петър Бойваленков, директор на Института по математика и информатика към БАН, академик Петър Кендеров, директор на Ученическия институт по математика и информатика, академик Юлиан Ревалски, директор на Математическия център по Международния център по математически науки в София и господин Арну Боберо, аташе по култура и въпросите за висшето образование към Френското посолство. Сега бих искал да дам думата на домакина на събитието, директор на Института по математика и информатика на БАН и ръководител на Национална програма Образование с наука, член-кореспондент професор Петър Бойваленков.
Уважаеми госпожи и господа, уважаема госпожо председател на Българската академия на науките, скъпи гости, скъпи ученици и учители, за мен е чест да открия това събитие, което е поредица от срещи, представлява поредица от срещи, лекции и вдъхновяващи разговори с изтъкнати представители на френската наука. От името на Института по математика и информатика ви приветствам с добре дошли и ви благодаря, че избрахте да споделите този ден и тази седмица с нас. Събитието, което ни събира днес и тази седмица, е повече от академичен обмен. То е свидетелство, доказателство за жива връзка между култури, между народи, наука, образование и поколения. Позволете ми да отправя най-сърдечни благодарности към нашите партньори в организацията, Френското посолство в България, Френския културен институт, които не само подкрепиха тази инициатива, но я превърнаха в реалност. В тяхно лице виждаме устойчив партньор и споделяме техния стремеж да отворим науката към обществото и да изградим мостове между българската и френската академична култура. Искам също така да ви приветствам и от името на Съюз на математиците в България, които са наш неизменен партньор и съюзник в усилията ни да отворим науката към обществото, да изградим мост към младите и да ги привлечем към науката. Науката има нужда от млади хора, решавачи на задачи, търсачи на отговори и може би и мечтатели. Именно за това ние участваме и подкрепяме програми като Образование с наука, което е национална програма на по-малко от година, но прерасна в такава от поредица проекти, които имаха с Министерството на образованието и науката. Подкрепяме и ученическия институт, който първо възникна като ученически институт по математика и информатика към нашия институт, а сега е ученически институт на БАН. Днес сред нас са представители на училища, на водещите училища в София, макар и СМГ да закъснява, но тук сред нас са основно представители на Националната природно-математическа гимназия. Също би трябвало да има от първа част на математическа гимназия, може би от френската гимназия, френската езикова гимназия. Благодаря най-вече на учениците, но и на директорите и учителите за съдействието и за интереса към това мероприятие, за участието в него. Присъствието ви е важен знак за нас и важна подкрепа. Особено ми е приятно да приветствам специалните гости на днешната и тази седмичната инициатива. Трима изтъкнати френски учени, чието присъствие тук е чест не само за нас, но и за цялата академична общност. Професор Бернар Тейссиер от Математическия институт Джусио към университета в Париж, чиято лекция ще чуем след малко, е забележителен учен с огромен принос в алгебричната и комплексната геометрия, с дългогодишна отдаденост към популяризирането на науката, научната комуникация и международното сътрудничество. Неговият ученик, професор Патрик Попеско-Пампо от университета в Лил, е изследовател с ярък почерк в теорията на особеностите, човек, който намира вдъхновение в пресечната точка между наука и култура. Не случайно той често свързва на математиката с изкуството, архитектурата и философията. След 2 дни в сряда ще посрещнем и професор Седрик Вилани, носител на Филцов медалист от 2010 година. Знаете, че Филцовият медал е еквивалент на Нобелова награда в математиката. Той е член на Френската академия на науките и професор в университета Клод Бернар в Лион. Професор Вилани не е просто математик, той е истински посланник на науката, обществена фигура и човек с мисия да превежда езика на абстракцията в език, разбираем за обществото, разбираем за всички нас, включително и за не-математиците. Скъпи ученици, вярваме, че беседите ви с тримата изтъкнати френски учени ще бъдат интересни и полезни за бъдещото ви развитие. Каним ви не само да слушате, но и да питате, да мислите, да участвате. Нашите френски гости не са тук да изнасят лекция от катедра, както също аз сега правя. Техните лекции би трябвало да са по-живи и те ще споделят пътя си. Как се става математик, какви предизвикателства и вдъхновения съпътстват търсенето в техния опит, в това, което са видели в други колеги математици. Какво е усещането да си част от световната изследователска общност? Надяваме се, че за много от вас днешната среща ще бъде една първа стъпка в науката, едно вдъхновение, което ще ви дава сили за напред. Вярваме, че науката се гради не само върху формулите, които всички трябва да прилагаме правилно, но и с човешко отношение. Именно за това намираме този формат, в който ще протече визита тази седмица, за толкова ценен. Благодаря за вниманието, желая ви вдъхновено участие и откривам срещата.
Благодаря ви, професор Бойваленков. Бих искал да поканя за приветствено слово господин Арно Буберо, аташе по въпросите за наука и висше образование към посолството на Франция в България.
Bonjour, je vais parler en français et mon collègue Branimir Genev, qui travaille avec moi à l'Institut français de Bulgarie, traduira mes propos en bulgare.
Аз ще превеждам на български, господин Боберо ще се обърне към вас на френски език.
Et donc je commence par vous prier de m'excuser de ne pas assez maîtriser le bulgare pour pouvoir parler directement dans cette langue.
Моля, извинете ме, че не владея български език достатъчно добре, за да мога да се обърна на него към вас.
Madame la présidente de l'Académie bulgare des sciences, monsieur le directeur de l'Institut de mathématiques et d'informatique, monsieur l'académicien Revalski, chers amis, chers collègues, chercheurs, enseignants, étudiants, lycéens.
Госпожо председател на Българската академия на науките, господин директор на Института по математика и информатика към БАН, господин академик Юлиан Ревалски, скъпи колеги, приятели, съмишленици.
Et bien sûr, nos hôtes, monsieur Bernard Teissier et monsieur Popescu Pampou.
И разбира се, професор Бернар Тесие и професор Патрик Попеску Пампу.
Au nom de l'ambassadeur de France, son Excellence monsieur Joël Meyer, et au nom de monsieur Luc Lévy, directeur de l'Institut français de Bulgarie, je veux vous dire que c'est un grand honneur pour nous d'être partenaires et associés donc à ces rencontres entre d'éminents mathématiciens français et bulgares et de brillants élèves et étudiants des lycées de mathématiques de Sofia et de l'Institut de mathématiques de l'Académie bulgare des sciences.
От името на посланика на Франция, негово превъзходителство господин Жоел Мейер, и от името на господин Люк Леви, който е директор на Френския институт в България, бих искал да кажа, че за нас е чест и голямо удоволствие да бъдем асоциирани към тези срещи между три блестящи френски математици, техните български колеги и брилянтни ученици и студенти от гимназии по математика и Института по математика към БАН.
Lorsque nous avons évoqué ce projet il y a un an avec monsieur le professeur Teissier, nous avons tout de suite accepté de nous y joindre et de le soutenir parce que c'est un projet qui d'évidence entrait dans les missions de l'Institut français de Bulgarie d'encourager la coopération entre la Bulgarie et la France dans le domaine des sciences et de l'enseignement supérieur.
Когато господин Тесие се свърза с нас и ни предложи да се включим в този взаимен проект за обмяна на опит, ние веднага приехме, защото смятаме, че тази обща работа е от полза за науката и за нашите двустранни отношения.
Ce sera donc avec beaucoup de plaisir que nous vous accueillerons au sein de l'Institut français de Bulgarie vendredi pour la dernière session de cette séquence d'événements pour partager autour d'une question qui est fondamentale: pourquoi devenir chercheur?
Затова този петък ще ви приемем с удоволствие в Френския институт, за да обсъдим защо всъщност тази тема е толкова важна за нашето двустранно сътрудничество.
Mais d'ici là, nous voulons surtout vous souhaiter une belle semaine de discussion, d'échange entre bulgares et français autour de ce langage que vous avez en commun, qui est celui des mathématiques.
Но сега бих искал да ви пожелая да прекарате една чудесна седмица и да ви пожелая също така едни плодовити срещи и дискусии във връзка с този красив език, който е математическият. Добра седмица на всички, благодаря ви.
Благодаря ви, господин Боберо. За мен е чест да поканя на сцената председателя на Българската академия на науките, член-кореспондент Евелина Славчева.
Уважаеми член-кореспондент Бойко Ленков, директор на Института по математика и информатика, уважаеми академик Ревалски, уважаеми представители на Френското посолство, уважаеми гости, лектори и участници в тази прекрасна среща и най-вече скъпи млади хора с интерес в областта на математиката. Много се радвам да видя в тази историческа зала професор Марин Дринов, толкова много млади, удохотворени лица. Млади хора, които най-вероятно ще поемат своя път в някоя от многобройните направления на математическата наука и практика. Институтът по математика и информатика към Българската академия на науките е един от най-старите и най-големи институти в академията. Това е институтът, който не само провежда фундаментални и приложни изследвания в различните направления на математиката, от математически структури през информатика и съвременни направления, като например изкуствения интелект. Но това е институтът в Българската академия на науките, който има най-голям опит и най-много активност в областта на образователните програми. Това е институтът, в който още през 2000-та година беше основан ученическия институт към Българската академия на науките, УЧИБАН, и днес това е име, което е известно в цяла България. Ние сме много горди с този институт, защото той започна като институт, който търсеше и развиваше таланти в областта на математиката, но днес там има и други секции, вече са 6 на брой и други природо-математически науки са включени. Едни от най-хубавите събития в тази зала са именно сесиите, които този институт провежда, и голямо достоинство и предимство на хората, които всеотдайно работят там, е, че те обикалят страната и търсят таланти из цяла България, работят с младите хора и привличат будните умове към науката и към Българската академия на науките в частност. Математиката безспорно е науката на науките и тя има връзка както с различните природни науки, така и също с философията, музиката, във всички сфери всъщност на познанието. И аз нямам съмнение, че този, който посвети професионалния си път на математиката във всичките и нейни разнообразни приложения, ще бъде човек с свободен дух и свободен ум. Мисля, че форматът, в който това събитие се провежда, също е много показателен. Говорим за срещи, за беседи, за дискусии, за лекции, но като че ли на последно място. Най-важното в тази серия от срещи с изтъкнати френски математици е именно достъпът да задавате свободно своите въпроси, да питате както за математиката, така и за усилията, които изисква посвещаването на нея, но и за удовлетворението, за удоволствието от тази гимнастика на ума и от това любопитство към знанието. Нямам съмнение, че развитието на съвременните дялове на математиката и особено развитието на изкуствения интелект ви дават представа за необятните възможности, които тази наука крие, но и за отговорностите, които това поставя пред нас. Така че, за да не отекчавам с едно дълго слово, бих искала от цялото си сърце да ви пожелая тази серия от срещи да бъде едно удоволствие, да запали във вас още по-силно пламъка на любовта към математиката, и бих искала да ви уверя, че Българската академия на науките винаги е с отворени врати за млади, будни, умни и щастливи хора. Желая на всички ви, както каза и господин посланника, аташето, да имате една страхотна седмица и в петък да споделите своите впечатления и своите планове за бъдещето. Благодаря на всички. Успех!
Благодаря ви, професор Славчева. За нас е истинска привилегия да провеждаме нашето събитие в академичното сърце на столицата, Българската академия на науките. Имам удоволствието да поканя академик Петър Кендеров, директор на Ученическия институт на БАН, за кратко приветствено слово.
Славчева, благодаря за хубавите думи, които казахте за ученическия институт на БАН. Аз ще поправя обаче Антони Рангачев. Не съм директор от много отдавна и не искам да бъда такъв. Аз като научен ръководител съм на ученическия институт на Българска академия на науките, който възникна, както беше казано, като институт по математика и информатика, но толкова успешно се разви, че от 2014 година решихме да го разширим върху другите естествени науки, както и върху хуманитарните и обществените. Така че всичко е включено и за сега този институт се развива добре. Аз искам малко да послаба очакванията, които може би много от вас имат, че като дойдат тук, това е така ще разберат как се става изследовател в областта на математиката и информатиката. Не е необходимо да мислите, че ще станете изследователи в смисъл научни работници. Ние много бихме се радвали, ако станете, но дори и тези, които няма да станат научни работници или изследователи в собствения смисъл на думата, ще спечелят от участието в тия дейности, които присъстваме днес. Защо? Защото такива времена дойдоха, че каквото и да учим в училище или в университета, след 10 години устарява. Можем ли да върнем цялото общество обратно в училище или обратно в университета, за да го доучваме? Нови неща има. Ами не можем, няма капацитет. А и да имаше капацитет, новите неща ги няма още в учебния процес. Защото образователната система е много консервативна. И в училище, и в университета се учат неща, които са утвърдени с вековете. Какво да правим? Единственият начин човек да не изостане от света е да се учи сам. А кажете ми сега, какво прави човек, когато учи сам? Търси информация, пита познати специалисти, обръща се да направи някакви експерименти, в интернет търси допълнителна информация. Ами, точно това правят и професионалните учени. Дейността е същата. Ученето сам е изследователска дейност, при която човек научава нови за себе си неща, а нашия опит от ученическия институт показва, че понякога получава и резултати, които не са известни на света. Нови научни резултати. Тогава се вижда, че е важно човек да придобие изследователски навици отрано и когато има такива навици, неговото знание никога няма да остарее, защото каквото дойде ново, той го усвоява. И като фалира фирмата, в която работи и остане на улицата без работа, лесно може да научи нови неща. И това е ученето през цялия живот. То почива, самостоятелното учене почива на изследователски навици. Затова е добре да участвате в такива дейности и да се научите на тях още от най-ранна възраст. Аз ви благодаря за вниманието.
Благодаря ви, академик Кендеров. Тази вечер сред нас са двама от лекторите. Професор Бернар Тесие, чиято лекция ще чуете съвсем скоро, и професор Патрик Попеско-Пампо. Професор Вилани все още не е сред нас, но искам да ви кажа къде в момента се намира той. Той започна своето пътешествие до България с влак от Париж вчера, след обед. В момента, по мои изчисления, се намира някъде в Унгария на път за румънския град Крайова. Очакваме утре сутринта да прекоси река Дунав и с влак от Видин да пристигне при вечер в София. Надяваме се, че ще дойде на време. Сега искам съвсем набързо да ви разкажа каква ще е програмата. Програмата може да я намерите на сайта на Института по математика и информатика. Там, където е новината за събитието, има и PDF файл, в който е разписана подробно програмата на събитието, но аз ще я преразкажа съвсем набързо. Първата лекция ще е изнесена от професор Тейссиер. Във вторник професор Тейссиер има среща с ученици в Националната природо-математическа гимназия, а по-късно от 16:30 ще чуем първата лекция на професор Патрик Попеско-Пампо. В сряда професор Попеско-Пампо ще има среща с ученици в Института по математика и информатика. А от 16:30 предстои да чуем лекцията на професор Вилани. В четвъртък професор Вилани ще се срещне с ученици в СМГ, само ако те дойдат на лекциите, а по-късно след обед предстои да чуем втората лекция на професор Пампо. И последната среща е предвидена за петък от 15 часа в Френски институт, който се намира на площад Славейков, да не объркате адреса случайно. И тази среща ще е свободна дискусия с нашите лектори, посветена на събитието, на която каним всички желаящи да присъстват. Сега имам удоволствието да представя нашия първи лектор, професор Тейссиер. Получава своето образование в Екол Политехник в Париж. Научен ръководител на дисертационния му труд е филдсовия лауреат Тейссиер Хиронака. Като голяма роля в научното развитие на Тейссиер оказва други двама легендарни математици – Оскар Зариски и Рене Том. През 80-те години на миналия век професор Тейссиер е неформален лидер на групата Бурбаки, в която са членували някои от най-видните френски математици на 20 век. През 90-те години е директор на института Анри Пуанкаре и на Федералния институт по математика в Париж. Професор Тейссиер е фелоу на Американското математическо дружество и е почетен член на Испанското кралско математическо общество. Отличията на професор Тейссиер включват ПЕКО лекция, заедно с филдсовия лауреат Ален Кон и наградата Жан Райну на Френската академия на науките. The floor is yours, професор Тейссиер.
Thank you very much. Good afternoon. I'm very happy to be back in Sofia, and I want to thank the institutions and the people who made this event possible. The Mathematics and Informatics Institute of the Bulgarian Academy of Sciences, and especially Professor Oleg Mushkarev, who was in this story from the beginning, Antony Rongachev, whom you've just heard, without whose energy of enthusiasm, probably this would not have happened, the French Institute and the French Embassy for their help, support in all matters. Hopefully, this lecture marks the beginning of a conversation between mathematicians and high school students, I mean research mathematicians and high school students. But it will depend on you, the high school students. I want to talk about about length, area, and wait a minute. I need to learn to do length, area, and volume. I begin with a quotation of D'Alembert because I'm going to try to convince you that algebra can be used in geometry in ways perhaps that are new to you. So begin with the estimation of length, of distance, is certainly as old as moving living beings. However, measuring length is certainly as old as numbers, measuring steps and this kind of thing. The first units of measurement we know about, at least in the Western world, are the step, the cubit. The cubit is the length from the elbow to the end of the longest finger, the foot, the handspan, the last part of the thumb, called an inch, which exists still today. The inch was divided in 12 lines and 144 points, and as you certainly know, 144 is the square of 12. But so there are other units. You could also count by days of walking, months of walking, but having well-defined units is not sufficient. One must find ways to measure effectively, including objects to which you do not have physical access. This is where the theorems of Euclidean geometry, which relate length and angles, come into play, added to the fact that length is invariant by translation and rotation, in the plane as in space. For example, you can measure the height of a tower by measuring the angle between the ground and its summit from a point at a given distance from its foot, and using trigonometric functions, such as tangent. There's a picture which shows a high school student in the Middle Age measuring the height of a tower. You see that he's measuring an angle with this object. This tells you in Latin that this is the distance from him to the foot of the tower. And then he's computing the height of the tower. There are many, many other ways of measurement. There is a whole novel by Jules Verne called The Adventures of Three Russians and Three British in Africa, where they measure the length of a meridian, and they use triangulations all the time. They build triangles, make angle measurements to compute the length of the meridian is the length of a weld between two places of which you know the latitude. You want to measure what is the distance. Okay. This why trigonometry is so important. Now let's come back to measuring the length of a curve, for example. So how do you do that? Well, you take straight lines, small segments, which are not too far from the line, which share points with it, and you add the length of those segments, like this. Of course, if you take shorter segments, you will get a better approximation to the curve. You take them shorter and shorter, you get a sequence of measurements, and in the end, you see that this sequence tends to a number which will be the actual length of the curve. You can take any unit, you measure the length of the segment, whatever, a centimeter, meter, and in the end, you will have the length of your curve as a limit of measurements. Now, there are some cases where this does not work, but in the last 100 years, mathematicians have found ways to give a length to even very complicated objects like this. They are called fractals. If you think of the curve, which is the boundary of this domain, you can see that it will be very, very, very difficult to measure it in the way I just mentioned. In fact, if you start to do it, you will find a sequence of numbers which tends to infinity. But now mathematicians know how to give a meaning to all this and actually give it a length, which will not be, well, a different kind of thing. Let's change subject. Now, I come to area. I think area is one of the most striking mathematical discoveries. It's much more subtle than length, because length you can see for yourself. Area, if you have two lakes which are vaguely of the same area, up to, say, 20 or 30%, but they have very different shapes, you're totally unable to say which one is larger. So I think that area began to be very important when people started cultivating. In the ancient Greece, people estimated the size of a field or of a town by measuring its perimeter. In Homer's Iliad, perimeter means around measuring around, if you like, in Greek. So, the length of the boundary. In Homer's Iliad, which is 7th century before Christ, the measure of the size of the city of Troy is 10,200 steps. So, just the perimeter. And I love the story that Proclus reports court cases of members of Greek communities who, in the 1st century after death, decided to divide land equitably, but according to perimeter. And at the time of harvest, they had surprises. And some of them went to court because they thought it was not fair, that they had very long fields with a fairly large perimeter, but a very small area. So I say this fields with the same perimeter may enclose a very small area. Think of a field like this compared to a field like that. This one may enclose very, very, very small area. So this is to convince you that area is an important notion. It's a very important discovery that you could name something called area and attach it to some part of the plane. It's intellectually a step important. So how do you estimate the area? You must have in your mind some way of thinking, how do I measure an area? Well, you take some piece of which you know the area, for example, a square, and you try to fill up the part of the plane, the domain, with squares of a given size. And then you sum up, you count the number of squares, and you multiply that by the size of the square, which is the square of the side, and you get a number. Let's see how this works. Like this, on this picture. You see I've filled this domain with squares. Of course, this is not a good approximation, but I start with fairly large squares because, let us say I'm lazy. I get some number, and then I take smaller and smaller and smaller squares, and they get closer and closer to filling the area. And again, I get a sequence of measurements which will give me a better and better approximation of the real area. But at least in this way, imagine there is a concept of area, which is the limit of those numbers. And that's very important, because approximating an object of unknown size by objects of known size is a major method in all sciences. And mathematicians have developed many, many ways, very clever ways to do that. Physicists too, by the way. So once the notion of area is established, once you have in your mind the idea that you can attach a number, square meters or square inches or whatever, to a domain in the plane, then you start thinking that you can do the same for a volume, for a solid object in the space. Well, then the intellectual step is not so large. You just replace squares by cubes, and you proceed as well, in the same way. Take smaller and smaller cubes, or you might take other shapes, by the way. But you must take small shapes of which you know the area, and then you just count the number of them. So let me show you some pictures of how this is done. Look at the two pictures on the right. They show you how to approximate a solid body like this by small cubes, which you pile them up. And then what is new is that in this instance, the solid body has a boundary, which is the blue part which you see here. And this boundary also has a measure, which you have to take into account. You may be interested in understanding what is the boundary of this and that. So you can measure this boundary in the same way as you measure areas in the plane by filling it up with small squares. Of course, the approximation is a little bit different because the squares will not touch the surface in the same way, but the process works. So in this picture, you see how to measure the volume of this body and the area of its boundary, the upper part of its boundary, because of course it has other sides. But this picture is to explain to you how you imagine that you measure the area. And once you imagine it, you find ways of doing it practically, approximate better and better, and you get an approximation. But the important thing is that you think that the limit is something you can think about. The area, it's a number which I compute by approximation, but the number exists. So what I want to do in this lecture is present some relations between the area of a plane domain and the length of its boundary, and similar things for the volume of bodies and the area of their boundary. So the relation between area and perimeter of a plane domain is a very old subject of research, which was started in the West. I don't know about China or India, but in the West by Greek mathematicians around the 5th century before Christ. And they knew a lot about polygons and Euclidean geometry, which will not surprise you. So they calculated many examples of area and perimeters. And this was 6 centuries before the court cases mentioned by Proclus, which means that in those times, the science took a long time to percolate from the philosophers to the people who till the fields, something like 6 centuries. Anyway, experimentally, they found that there has to be an inequality between the length of the boundary, which is, as I said, called the perimeter, and the area of a plane domain. And this inequality is written on the screen. And nowadays, this is called the isoperimetric inequality. Reasons I don't know why it's called like that. Anyway, the Greeks knew by experience that equality in this inequality is attained only for the disk, the round domain, whose perimeter, as you certainly know, is 2 pi times the radius, and the area is pi times the square of the radius. And you can see that in this case you have equality in the isoperimetric inequality. So this means that for a given perimeter, the disk is the shape enclosing the largest area. And this is an idea which has been going through the minds of mathematicians for centuries, as I will explain in a minute. So, but before mathematicians really thought about this, everybody knew it. Why do you think the portholes of the ships or spacecrafts are round? Because the light coming in is proportional to the area, And the waves that come in, assuming the porthole is closed, comes in through the boundary. So you must have the smallest possible boundary length, perimeter, for a given area. The picture, this is a modern porthole. And it is round, although it's in practice, if you are a shipbuilder in the Middle Age, it's more complicated to make round windows than to make square windows. Okay, but still they did it because they knew that this was better to get less water inside if the, if the perimeter was not very, very waterproof. And same thing goes for spaceships, for submarines and everything. You want to have the maximum light, which is proportional to the area, and the minimum length of the boundary. Okay? So, as I said, this problem has been going through mathematics, but it laid quiescent, roughly speaking, between the 1st century after Christ until the 17th century. Not much work was done. But still it was there, in the background. So in a book called Le Problème des isopérimètres et des épiphanes, Tommy Bonnesen, who was a Danish mathematician writing in French, writes something like this. I forgot the exact quotation, but he says, for most people, about this maximization of the area for a given perimeter. He says, for most people, it's a matter of common sense. For the mathematician, on the contrary, it has been a cause of much reflection. So you can take this as a commentary on mathematicians, but I hope you do take it as a favorable commentary about mathematicians. And indeed, if you want a complete proof, which is valid even for relatively complicated but not fractal boundaries, the complete proof was given only in something like 1895. That's 2,500 years after the Greek mathematicians knew the results. They did not prove it, but they certainly knew it. So the proof had to wait 2,500 years. And the reason is that the analytic tools that were developed, which are essentially linked to what we call nowadays the calculus of variations, were developed mostly in the 18th and 19th centuries. And the mathematicians, being mathematicians, they wanted a proof which was valid in full generality, as they say, for any measurable boundary curve, any curve which could be measured in the way I explained before, roughly. Okay, so how do we prove it? Nowadays, there are several proofs of this fact, that the disk is the only plane domain which maximizes the area for a given perimeter, because even if you know that it does maximize, the mathematician is not happy until it is proved that it is the only possibility. It is the only plane domain which has this property. As I said, for most people it would be a matter of common sense, but mathematicians like to look at beyond the common sense many times. Anyway, I'm going to present you one of the proofs which has many applications in other domains. It belongs to a domain, to a way of thinking which has applications in many, many different domains of mathematics. in analysis, even in practical matters, as I will explain, like geology. Anyway, but before I do that, I need to introduce a completely different topic a priori. So I need to tell you about certain domains in the plane or in space which are convex. Convexity is a very important notion in mathematics. It's a very simple notion. A domain is convex if whenever you have 2 points in it, the segment which joins them, the piece of line which is between them, is still in the same body. I'm going to give you immediately an example. This is a plane domain which is not convex because if you take a point here and a point there, the segment which joins them is not inside. Okay, so let me go back a little bit. So in the line, a bounded convex subset is just a segment, an interval, the 2 points and what is between them. An unbounded convex domain, there exists also, is the whole line. It is convex. If I take 2 points in the line, the segment which joins them is still in the line. Or, for example, the set of points which are smaller than a given value. It has the same property or larger. But we'll be mostly interested in the bounded convex domain. Anyway, in the space, so unbounded convex domain, examples are half planes. So what is a half plane? A half plane is when you take, you take a line, just imagine that you have a line crossing the plane like that, and you take all the points which are on one side of that line, all the points in the plane which are on one side, on the other side. Those are called half planes for obvious reasons. If you want to to have equations, it's a set of points in the plane where some affine function of the point xy is of the form ax plus by plus c, where a, b, and c are numbers. And the set of points where this function takes negative values or positive values. Okay, so that's a half plane. They play a certain role in the theory, that's why I introduced them. Okay? So there are other convex examples of convex regions, like if you take a plane conic defined by a degree 2 equation, an ellipse or a parabola or a half hyperbola. There are also convex regions which are bounded in the case of the ellipse and unbounded in the other cases. And there is a reason for that, which we owe to Apollonius, which is that the three regions like that are the intersection in space of a cone and a plane. And the cone, the interior of the cone is convex, and when the intersection with the plane remains convex. So there are many, many examples of bounded convex regions. You take just any region, as I will explain, you can attach to it a bounded convex region, which is called the convex hull. But I will explain that on the next slide. The intersection of two convex domains is a convex domain, because if you take 2 points in the intersection, it belongs to both of them. So the segment which you use to join them belongs to both of them as well. And so it's still in the intersection. That means the intersection of two convex domains is a convex domain. Any bounded domain has a convex hull, which is a bounded convex domain. It is just the intersection of all the convex domains which contain it. In fact, and this is not quite as obvious, it is the intersection of all the half planes, or in space, the half spaces which contain it. So whenever you have a body, which may be what it is, you can attach to it a convex body which contains it, and it contains it is the smallest convex body which contains it. So this is to explain to you what a convex domain or a convex body is. Convex objects in mathematics are considered to be nice. Convex functions, convex bodies, they have many nice properties. Let us now look at the same example, but from a metric viewpoint. You can remark that if I take, so the part which is delimited with these dotted lines, that's the convex hull, if I look at that. And you can notice that the perimeter has decreased because the distance between these 2 points is less than the distance along the boundary of my original curve. Same thing here. So the perimeter has decreased, but the area has increased. So if I try to find bodies which have maximum areas with respect to perimeter, I can always restrict myself to convex bodies, because the other ones will certainly not be optimal in any way. Convex body has more area and less perimeter. I want just a point, I just give the explanation that this is because the line is the shortest distance between 2 points. So you take these 2 points, which are in some sense extremal points. They are the points where this body will meet some half plane like that. Imagine this line, you continue it, you get a half plane. So between these 2 points, the line is the shortest distance, so it will be better than what goes on along the perimeter. Okay, but this is not true in space. Just a remark. It's because there is a whole field of research called minimal surfaces, which minimize the area for a given bounding curve. But that's not our subject. Now I want to introduce to you the reason why I put the quotation of d'Alembert in the beginning. Remember, he said, algebra is generous. So we can produce an algebra out of convex domains or convex bodies. We can add them. This was discovered by Minkowski, who was a mathematician of the late 19th century and beginning of the 20th century. You just take a point in one convex body, a point in the other, and add them up as vectors. If I say vectors, it means I have an origin. So I choose an origin. The choice of the origin is not important. Why? Because if I change origin, it's like making a translation in space. And everything I'm talking to you about, the volume, the area of the boundary, the perimeter, all that is invariant when I move my body around. So I can choose my origin wherever I want. So you choose an origin, and you take a vector in one convex body, a vector in the other one, you add them as vectors, as you learn to do, at least in the plane, I hope. Now, so this is the Minkowski sum. I will give you an example in a minute. You can remark that when you have an origin like that, you can always make a homotopy. You have your domain or your body, and you just multiply all its points by some positive number t. You get a bigger body, and that's called homotopy. And it plays a role in this story. So the operations which play a role in this story is we take a convex body, we can add to it another convex body, but we can also multiply them one by a number, a real positive real number, multiplying all the coordinates by the same number. And it's very, very simple operations, but they turn out to play a very important role. So this is an example of the Minkowski addition of these two convex domains. You add a point to this, a point to that, and in the end, you get this. And then what I'm going to talk to you about is written on this slide. If I call A the area of this one and B the area of this one, I look at the area of the big one. I subtract the area of the first one. I subtract the area of the second one. I get a number which I call 2c for reasons which will appear later. And then there is an inequality which relates the square of c and the product of the two areas. And this is essentially the topic of my lecture. Why is there such an inequality? What does it mean? What can it be used for? I give you a simpler example. I take a hexagon and I add a homothetic of the disk of radius 1. Okay? So I call that TD, the bold-faced D designates the disk of radius 1 in the plane, so TD is a homothetic of it, so it means the disk of radius T. So I add to any point of K the disk of radius T. Of course, there will be many points where the addition will just remain inside K. But then if I take a point on the boundary, if I add the disk, I will move outside of the boundary, and the result of the Minkowski addition of my convex domain, to the disk is this new place. And if you try to compute the area of this larger body, well, you can see that it begins with the area of K, but then I add these rectangles. Each of these rectangles is the length of the side times its area is the length of the side times t. So in the end, I sum up the length of the sides times t. That gives me the perimeter times t. And then these little corners here, if you think about it, they add up together exactly to make a disk of radius t. This one, you see, they are exactly parallel. So if you put them all together, bring all these points here to the origin, you get a disk. So you get a disk of radius t. We know its area. It's pi times t squared. So you see that the area of k plus td is S, the area of k, plus L times t, where L is the perimeter, plus pi times t squared. Aha, this is interesting. So we can prove that this formula is valid when I ask to the TD to any convex domain in the plane. So this formula is valid not for the hexagon, but for any convex domain. And you can remark that the discriminant, this is a polynomial of degree 2 in T, and its discriminant is L squared minus 4 pi s. So the isoperimetric inequality is equivalent to the fact that this polynomial has real roots. That's a surprise. Something which is purely geometric, the isoperimetric inequality, turns out to be an algebraic fact, that some polynomial has real roots. I'm not sure we understand that completely even today. Anyway, so now let's see, usually mathematicians, to understand something, they try to generalize. So let us generalize a little. All this story remains true when I replace the disk by any other bounded compact set. So let me replace the disk by any, and for symmetry, I also make a homotopy on the first one, so I call them K1 and K2. And I compute the area of T1 times K1 plus T2 times K2. I remind you, this is a homotopy, this is a homotopy, and this is a Minkowski sum. And it is still true, with basically the same proof, that this area is what we call a homogeneous polynomial in T1 and T2. All the terms have degree 2, degree 2, degree 2, degree 2. And then, the important thing is there are coefficients. So V0, we know that if we take T2 equals 0, the area of T1 K1 will be the volume of K1 multiplied by T1 squared. So there is no surprise that V0 is the volume of K1, V2 is the volume of K2. But then the interesting guy is this one in the middle. And this one in the middle, in general, we don't understand very well. In fact, if you ask people to compute on a computer these numbers, turns out it's quite complicated. So we saw it very simple in the hexagon case, where this was just the sum of the areas of the rectangles. But if K2 is not a ball, it's a more complicated story. Anyway, what happens is that the same result which proves this also proves that the same inequality is true in this more general case. That is to say that V1 squared, remember this was the perimeter, but in our case it's more general, so V1 squared is at least equal to V0 times V2. And I write this inequality like this. V1 squared is larger than V0. This number V1 is called the mixed area for obvious reasons, and it is always positive unless K1 and K2 are points. But as I just said, if K2 is not a ball, the meaning of V1 is more subtle. Now, this brings us to the proof of the answer to the isoperimetric problem. So, our friend Bonnesen found a very beautiful result. For a plane domain, you can, any plane domain, so this is the blue part here, you can define the in radius, which is the radius of the largest disk which is contained in the domain. It may be that there are several disks with the same radius which are contained. We don't care, we just take that radius. Now, the out radius is the radius of the smallest disk which contains our domain. In this case, I believe it's unique. Anyway, so some people call it circumradius, or might call it out radius, never mind. And even the people who made this picture called it R out. So I hope it's clear. Any domain, in fact, convex or not, you see in this case that it's not convex, you can attach to it two numbers, the radius of the largest disk contained in it and the radius of the smallest disk containing it. Okay? And then one can prove that we have the following inequalities between the area of the domain, the length of its perimeter, the in radius, and the out radius. So these are beautiful inequalities which imply, if you take the difference of this, of the largest guy here and the smallest one, you find that the difference is square root of L squared minus 4 pi s, and you take everything to the square, and you find this inequality, which is the one which was discovered by Bonnesen by other methods. But never mind. This is Bonnesen's inequality. And what is beautiful in this inequality is that you can see immediately that if you have equality, if L squared minus 4 pi s is 0, then R has to be, big R has to be equal to small r, and your domain has to be a disk. No choice. This is an absolutely fantastic proof. Okay? Now, let me come back to just some comments on this. If instead of looking at the polynomial pk of t, I look at pk of minus t, this is just s, I just change the sign of t, so it's s minus lt plus pi t squared, then the picture which you must have in mind about Bonnesen's inequality is that you take the polynomial which measures the area of k1 plus tk2, you change t to minus t, and then the graph of pk minus 2 is this beautiful parabola, and Boneson's theorem implies that the in radius and the out radius are located between the roots. And the disk corresponds to the fact where the parabola has gone up and is in fact tangent to the t-axis, so the two radii have to be equal. So remember this. Okay, so the same is true when you replace the ball by any bounded convex set. But of course, you have to adapt the definition of in radius and out radius. You have to take the largest R such that a homothetic of K2 sits inside K1, and then the smallest R such that a homothetic of K2 contains K1 up to translation. So it's a bit more complicated. The ball has many advantages because it's symmetric. It's invariant by rotation. As soon as you lose invariant by rotations, things become a little bit more complicated, but in real life, you cannot always assume that your second body you're looking at is a ball. So, in the end, the same result is true. And this is not at all obvious, that we have equality v1 squared equals v0, v2 in our inequalities, which is so, only when k1 and k2 are homothetic. So this tells you something that mathematicians like. It tells you that the result that we prove for the isoperimetric inequality is not restricted to the ball. It's in fact valid for any two convex bodies in convex domains in the plane. And we like that. We like to understand that something is true more generally than what the original problem wanted. Okay. So I hope you begin to be convinced that D'Alembert was right, that algebra is generous. Now, to continue, we have to look at what happens in space. In space, the same thing is true, except that when you look at the volume of homothetic of bodies in space, it's a polynomial of degree 3. So we write it v0 t1 cube plus 2 v3 v1. There are reasons why we put 3 here, but I don't want to go into that. In this story, there are lots of binomial coefficients which come there because it simplifies very much certain things. So there is no real issue there. But bear with me. The important guys are v1 and v2 here. v3 is the volume of k2, v0 is the volume of v1, and these are the v1 and v2 are the important guy. They are called the mixed volumes for obvious reasons, and usually they are denoted like this. The things between brackets here tell you a degree of homogeneity. It tells you that if you multiply k2 by t, then this number is multiplied by t. But if you multiply k1 by t, then this number is multiplied by t1 to the power 3 minus I, which might be, if I is 1, for example, is t1 squared. Okay, this is the one here, and conversely. So it's a convenient notation to remind you what you're talking about, and it also is a memory of these people are homogeneous. If I multiply k1 by t, this one is multiplied by t cubed, this one is multiplied by t squared, and so on. Okay, so this is the person who plays the role of our degree 2 polynomial, which helped us for the isoperimetric problem. Is there something similar in space? That's an interesting question. Well, there is. So about this degree 3 polynomial, we have two main results, one which I can state precisely, and the other one not so much. But anyway, so the numerical result is a deep result in the theory of convex bodies called Alexandrov-Fenchel inequalities. It was proved in the 1940s. And it is that, you remember the inequalities we had for V0, V1, and V2 for plane domains? Well, we have similar inequalities between V0, V1, V2, and V3 in space. So these inequalities tell us something about the mixed volumes, and I'll tell you in a minute a little bit more about this. Anyway, if we look at the square of V0 over V1, it is certainly less than the product of these other two quotients. So that gives us V0 over V1 squared is less than or equal to V1 over V3. You see, when I multiply these two guys, I get V1 over V3. So we write this inequality like this. V1 cube is greater than or equal V0 square V3. Okay? So what does this tell us? Well, let's take for K2 the unit ball. Then the coefficients 3V1, which is the derivative at t equal, you certainly noticed that if I look at this polynomial, then take t2 equal 1, then I get a polynomial in t1, and, oh sorry, take t1 equal 1, because I'm adding the ball. So take t1 equals 1, then I get a polynomial in t2, and this term is the linear term, which means that if I differentiate the volume as a function of t1 and t2 with respect to t2, I get exactly 3 times v1, and take the value at 0. So you differentiate this polynomial for t1 equals 1 with respect to t2, take the value at t2 equals 0, you get 3v1. This is the algebraic equivalent of the fact that when you take a body in space, you add to it a ball, t times the ball of radius t, then you thicken it a little bit. Okay? You compute the volume of the result, and you want to compute the derivative for t equals 0. Well, to compute the derivative, you take the volume of the result minus the volume. Divide by t, and let t tend to 0. That's how you compute a derivative. Now you have the thickening, it has a certain volume, you remove the volume of k, you get the volume of the slice you have added, okay, around k, and then you let t tend to 0, and you see that this has to tend to the area of the boundary, just like it did for the hexagon which I showed you. This is a quite general principle. So the area of the boundary of a convex body in space is the derivative of the volume polynomial when I add t times the ball. That's a nice way to learn derivatives, because you can see what you're doing. Usually when you compute a derivative, well, no, it's not true. I was going to say something wrong. Anyway, we have these inequalities, and as I was saying, the coefficient 3v1 is precisely the area of the boundary of the body, k. So the preceding inequality, which we've just seen, becomes the cube of the area of the boundary is at least equal to 27. Remember, that's 3 to the cube, volume of k squared times volume of b. But we know, I mean, not all of us know, but people know that the volume of the unit ball in three-dimensional space is equal to 4 pi over 3. So we get the following, we just replace it in this formula. We get s cubed is at least equal to 36 times pi times the volume of k squared. This is exactly, for three-dimensional convex bodies, what we found in the plane. In the plane, we found L squared at least equal to 4 pi the area. Here, we found that the area of the boundary, but cube, because we are 1 dimension higher, some constant times the volume of k squared. This teaches you something really interesting about the boundary of a solid in space. You can at least have a lower bound for its boundary just for the volume, or maybe more interesting from the viewpoint of measurement. If you can measure the area, you can get at least a bound on the volume of your body. Its square is less than a constant times the area. Okay? So this is the isoperimetric inequality for bodies in space. Okay? Again, if we assume that k is convex, there is equality only if k is a ball. So we have this optimal character of balls also in the three-dimensional space. For the geometric results, I have to be somewhat vague because the computations are a bit complicated, but I can give you the idea. I told you that there is one mixed volume, this one, which has the homogeneity of, if I take T1 equals 1 again, let's say, this is homogeneous like T2 to the power 1, just T2, and then this one has the homogeneity of T2 squared. So this one behaves like the length of lines, and this one behaves like the surface, I mean the area of things. And it turns out that one can make this remark quite precise, but I cannot make it precise here, and that this volume, which is homogeneous of degree 2 in K, so it should behave like the area of the boundary, but it is not the area of the boundary in general. Oh, sorry, it's the area of the boundary, but also the average area of the orthogonal projections of K to planes. So you take your body in space, you project it to a plane orthogonally, you get some domain in the plane, and you compute its area. Now, if you take lots and lots of different orthogonal projections, and you compute the different areas of the projections, then you have to normalize, that means taking an average, and you find out that this average is also what you computed as the area of the boundary, and that's a nice explanation for the behavior of these mixed volumes. And similarly, for the projection onto lines, when you compute the length of the projection of your body to lines. So this is what people do, try to understand how the size of an object in space can be estimated or guessed at from looking at many of its projections. Because suppose you want to know, suppose you have an asteroid, suppose it's convex, which is not generally the case, but suppose it's convex. And all you can do with your spaceship is take pictures from outside. So you can take many pictures, and then you compute the area of the image you get. And it tells you something about the volume of the, at least a bound on the volume of this object. So this is interesting. And this is what they do. I mean, in fact, we forget that people, like, for example, in space science, they use this kind of thing all the time. Now, the average area of the intersection with K with affine planes, which is another thing we do, project a body to planes or cut a body by planes. Again, you get a domain, which is convex because it's the intersection of a convex body with a plane. And we want to know what is the average area of those intersections. And these are again determined by the mixed volumes, which I mentioned earlier. But the formula is a bit complicated to explain. Okay, now I want to talk about a different result, which I find very beautiful, which is totally related to this, but still different. You may ask yourself, is there another way of measuring the size of a domain or of a body in space, which is invariant by translation, by rotation? Is there another way than taking the volume for a body in space, or the area? Is there another measure which I have not thought about? Because we found the area, we thought it was a very beautiful and powerful concept, but is there another concept, completely different, which is also invariant by translation and by rotation? Maybe, we don't know. As a mathematician, we say we don't know, so we have to find out. Let us find out. This is what Hadwiger did. Hadwiger was a Swiss mathematician of the last century. So you have first, as a mathematician, you have to explain what you are looking for. So what we are looking for are called valuations. This is actually a special case, but never mind. It's something which associates to any convex domain or a body in space a non-negative real number, which has the property that the value of this function on the union of two convex sets, mind you, this is not convex anymore in general, but never mind, is the sum of the volumes minus the volume of the intersection, of the value, sorry. So the valuation of a union is the sum of the valuations minus the valuation of the intersection. If you make a picture in your mind, you see immediately that this is true for volume. Okay? And in addition, we ask what I said earlier, that I ask that this valuation on convex sets is invariant by rigid motion. Rigid motion means a combination of translations and rotations. So the volume does that. Okay? It turns out that the mixed volumes, which I told you about, also do that. Good. It's not so surprising because I told you if you take orthogonal projections and sections, all that is invariant, is additive and invariant by translation. So they all do that. But the theorem of Hadwiger is that anything which does that is actually a combination of mixed volumes. It says any valuation, as I've explained in the beginning, any valuation, it has to be, in addition, it has to have some continuity with respect. If you deform the volume or the area a little, the valuation has to move a little. It's a technical thing, but it's important. Or you can replace it by the fact that if you have K1 contained in K2, then the value of K1 has to be less than the value of K2. So this is easier to visualize. So the theorem of Hadwiger says that any valuation, I wrote in the plane, but that's in space actually. In the plane or in space, any valuation is up to an additive constant, a combination of area and perimeter. In the plane, sorry, I wrote too fast. I read too fast. In the plane, so I don't know why I wrote 3 minus I. Anyway, the theorem is that any valuation is a combination of the mixed volume with real coefficients. Same thing is true in the plane and true in space. Any valuation in space is a combination of mixed volumes with the ball. And in particular, the area and the volume are up to multiplication by constant, the only valuations which satisfy that when I do the homothethy on K, it's multiplied by T squared, and the homothethy in the space is multiplied by T cubed. So this is a complete characterization of all the functions which look like the volume, which are valuations, that means they are additive. So most of what I've shown you, and in particular Hadwiger's theorem, extend to arbitrary dimensions. It even extends to much more geometrically complex bodies, which are called polyconvexes, which are finite unions of convex subsets in affine space. Okay. Any questions so far? Now, I go to a different topic, which is still in the same general realm. And it says, suppose you have a curve like this. I hope you can see it. Suppose that curve is in an area where you cannot uncoil it. It's bound, it's in a room. You cannot uncoil it. But still, you want to estimate its length. It's very important for you. You have to use it to make a bridge or something. And you really cannot physically uncoil it. Is there a way to estimate the length? Well, there is. It's called Crofton's formula. And Crofton's formula tells you that the length of a plane curve is proportional to the average number of its points of intersection with lines. So in formula, it goes like this. The length of C is a constant times the integral of, these are the number of intersection points of C with L. A is a constant which has to be chosen. But I just want to give you the idea. What this means is that if you look at this curve and you want to measure its length, you first make a test curve, which can be like the curve in S, which I showed you about measuring the length. And you measure its length by intersecting with many lines in the plane. So you count the number of points of intersection. This will give you a norm. Then you take this norm, which will compute this. What I mean is that this will compute for you the constant A. Then you take this constant A, and you take, say, 40, 50 straight lines, and you cut them through your plane curve like that, and you count the number of intersection points, which is feasible, I mean, physically feasible, even in this curve. You have to be a bit patient. But then, once you've done that, you have an estimate of the length of your curve, which can be fairly precise. Even if the curve is complicated like this, if you take 50 lines, you get I don't know the exact results, but I know people have computed that. And the precision is really surprising. It's much better than what one expects. So if one day you find yourself in an expedition, you have to make a bridge over a river somewhere in the Himalayas, and you only have a rope like that, which turns out to be lying out in a room, and it's so heavy that you can't really uncoil it, but you want to know if it's long enough to cross the river, you do this. Okay. This, I want to mention, special case of results which have many applications, not only in mathematics, but for example, this kind of thing helps, this kind of formula measures not only length, but also areas and volumes. For example, people use it to estimate the volume of pulmonary vesicles, or the area of the lungs, things that you cannot easily compute, by just spreading out the lung. The average volume of the pores in a porous medium. You know, this is important in geology because it tells you a lot about the nature of the medium. It's also important in oil prospection because oil exists in porous media. And for the technicians, it's very important to know the average volume of the pores of this medium. There are many, many, many other applications of this kind. And to finish, I want to show you what all this story, which I hope I've made understandable, how it could be written from the viewpoint of a professional mathematician. So I give you the vocabulary. So the vocabulary will say DL. DL is the guy here in the integral. So for the mathematician, this is an invariant measure, which is unique up to multiplication by a scalar, that's a theorem, on the space of affine lines in the plane. So you take the plane, and you think of all affine lines in it as points in a space. Okay? It's difficult to imagine, but you have to do that. And it turns out it's not so difficult, because what is an affine line? Basically, it's ax plus by plus c equals 0. So a, b, and c characterize the line up to multiplication by a non-zero scalar. Okay? So you already have coordinates in that space. You don't know what it looks like, but you have coordinates. But you can even know what it looks like, because what is a line, an affine line? It's a direction and a point on it. Okay? So the space of all affine lines is the space of points in the plane, that one we know, it's the plane, and the space of directions. What are directions? A direction is a line through the origin. A line through the origin is characterized by its intersection on a half circle, except that the two extremities of the half circles have to be identified. So what does that look? A half circle with the extremities identified, it looks like a circle. So you can think of this space as the product of a circle by the plane. So you can have a picture of it. And then you must imagine that on this space, which is not completely obvious to imagine, but on this space you have the equivalent of the measure of an area in the plane, or a volume rather, because we're in 3 dimensions. We have the equivalent of the measure of a body in 3 space. We have a space of dimension 3, which is not our 3 space, but it still exists and we can describe it. And we have in that space the analog of the measure of a body. And that is our, and it is invariant when we make translations and rotations. So this is an invariant measure on the space of affine lines, which is called the affine Grassmannian, which, as I just explained, is the product of a circle of directions by a plane. Now, in that space, this space, remember, a point in this space is an affine line. So now I can look at my curve in the plane and looks at the points in that space, that means affine line, which intersect my curve. This is a subset of the set of affine lines. Certain set of affine lines, those which intersect my curve. So this is like a domain in 3 space. So to my curve, I have associated a domain in this new 3-dimensional space. Now, this space is measurable. So that's a technical notion, because I had a measure. I have to know what sets are measurable. And then the function, which to a line associates its number of intersections, integrable. So all these, I'm telling you all these technical terms because this is the way you would find the story I just told you in a book written by a mathematician. And finally, the integral, that's my integral here, is a linear function of the length. Okay? So put a on the other side, call it 1 over a. It tells you the integral is a linear function of the length. So I've told you in the language of professional mathematicians, the story which I just told you about measuring the length of a curve in a room in which you cannot uncoil the curve. This is about, so the domain which I've been telling you about has several names, which in itself shows that it has to be interesting. It's called integral geometry or geometric probability. I won't explain geometric probability because it's connected to, well, I can tell you in one sentence. If I have a convex area sitting in another convex area, and I throw points in the larger convex area, I throw points at random. That's why probability. Then knowing that the points are in the larger convex set, what is the probability that it actually lands in the smaller convex set? So that's the ratio of the volume, of the area, sorry. So this has to do with, there are many forms of probability which come into it, but if you want to look at it from purely geometric viewpoint, it's called integral geometry. And as I said, this is to finish things you will learn if you continue to study mathematics. Thank you very much.
Thank you, Bernard, for this beautiful lecture. Any questions, comments? Sure, wait.
My question is, can you please repeat how we choose the constant a when we are calculating or estimating the length of the curve?
But I explained...
Bernard, you can use the whiteboard to draw.
I explained in the beginning that you have to normalize. You have to... As I said, the measure is defined up to a multiplicative constant. So you have to take a curve of which you know the length, and then compute the volume of the space of lines which hit it. And that gives you the constant A. But you don't have to do it with the curve I showed. You can do that with any very simple curve, like a circle or whatever. So this will give you the constant A. The ratio between the number of points of intersection and the actual length, you can test on a very simple curve.
So I have a question regarding mixed volumes. Is there a way to visualize them?
There are computer programs which show you the mixed volumes, show you volumes on which the mixed volumes are available. In fact, if you take, they work on it for polyhedra, of course. Maybe I should stay behind the mic. They work for polyhedra. Mm-hmm. If you take the Minkowski sum of two polyhedra, in general it's very complicated to compute, but there are programs which will do that for you. The thing is, if you take polyhedra, polyhedron is the convex hull of a finite number of points in space. And if you add two polyhedra, so the points we are talking about are called extreme points. Of course, if you take the convex hull of a certain number of points, they are not all extremes. There will be some which will be in the convex hull of other. But forget about that. Then when you take the Minkowski sum of two polyhedra, we know that their extreme points are the sums of the extreme points of the two polyhedra. Okay? But then people compute the volume, and they found ways to re-subdivide in such a way that the mixed, some sub-polyhedra of the sum appear as guys whose volume will give you the mixed volume, just like generalizing what I showed for the hexagon. But this is very complicated. In general, the shapes you get, at least those I've seen, they're not very intuitive.
So we have only visualizations for
polyhedra.
For polyhedra, okay.
As far as I know. No.
Other questions? You can ask about anything. Yeah.
I make some comment, not a question. Many years ago, I taught some course, and the student asked me how to explain to my girlfriend what you study. And I explained that the coordinates, the first coordinate, this is the street where you live. The second coordinate, this is the number of the street, of the house. And the third, this is the floor which we study. Okay, okay, this is very clear. I explained this to my girlfriend. But you see, there is something which I want to say. Einstein would say that you really understand something if you can explain it to your grandfather. Your grandmother.
Okay. Other questions?
Thank you for a very inspiring lecture. Indeed, this is a classical mathematics, but not Greek mathematics, already very close to our time and very inspirational mathematics. Are there some connections with tomography? Because you mentioned...
Yes. As I was saying, these formulas relating... So tomography, for those of you who do not know, is a method consisting of making pictures of opaque parts of the bodies by sending rays, the rays, whatever nature they have, through them, and then each ray is attenuated by the opaque body. And there is a beautiful theory called the radon transform, which tells you if you send many different rays, you can compute an image of the body, you can reconstitute an image of the body. And what you want to know is, first, its volume. It's very important in medicine sometimes to compute the volume of organs. And in some cases, as I said, for the lungs, you want to compute the mean volume of the alveoles in the lungs. And all this is a mixture of tomography and integral geometry, actually. Because integral geometry does not tell you how to reconstitute a shape just from the attenuation of rays. That is not a theorem of integral geometry. In fact, it's computing, looking at the effect on integrals, but it's not part of what I've told you about anyway. But this is very closely related, and they are both used in, as I said, used a lot in medicine for medical imaging. All these theories play a fundamental role.
Не се притеснявайте да задавате въпроси. Може да питате професор Тесие за каквото си помислите. Да.
I wanted to ask, are there any other evaluations except for volume?
That's an excellent question. Yes. But, Hadwiger's theorem concerns valuations with values in the reals. But you can take valuations with, you see, what I did is volume of K1 plus K2 minus volume of K1 equals volume of K1 plus volume of K2 minus volume of the intersection. But you can apply that in any group. And so there are valuations with values in different groups. For example, there is one with values for a body in 3 space. There is one with values in 3 space itself. 3 space is a group. You can add points, as I've shown you. So you can associate to a convex body something which is called its Steiner point, which is a kind of center of gravity defined in a fancy way. And the center of gravity is not evaluation, but the Steiner point is evaluation from the space of convex bodies to 3-dimensional space. And there are other examples, but there is none that comes up. I know there are many other examples, but no one comes to my mind. I have not prepared the answer to your question.
But tomorrow we have an informal discussion with Professor Teissier in NEPMG And so tonight he will prepare something for you.
Yeah.
Patrick, are you going to talk about Steiner points tomorrow? Okay. Any other questions? Okay, so let me remind you, as I said, that tomorrow we continue at the National Gymnasium of Natural Sciences and Mathematics at 1 o'clock. So we hope to see you there. It will be an informal discussion. You can ask Professor Teissier about his career path, what made him study math, where he derives his inspiration for mathematics. Of course, you can ask questions about the lecture. So we hope to see you tomorrow. Okay, thank you, Professor Teissier.